somewhere in the mountains of northern Chile, a machine just opened its eye, and it hasn't blinked since. Every 40 seconds, it takes a picture of the sky. Then it moves. Then it takes another. It doesn't stop for clouds, it doesn't stop for storms, and it will not stop for the next 10 years. In its first few weeks of operation, before it had even officially started its real mission, it found over 11,000 objects in our solar system that no human being had ever recorded. 33 of them were asteroids on orbits that bring them close to Earth. It has already sent out 800,000 alerts in a single night. By the time it's done, it's expected to send 7 million alerts every single night, flagging explosions, vanishing stars, and objects moving through the dark that we've never seen before. This isn't a satellite. It isn't a probe. It's a telescope, the most powerful one ever built, and it was just switched on. What it's already found in its first weeks should unsettle you a little. What it's built to find over the next decade should unsettle you a lot more. High on a mountain called Cerro Pachón, nearly 9,000 feet above sea level, the air is thin, dry, and almost perfectly still. It's one of the darkest places left on Earth, which is exactly why they built it there. The Vera Rubin Observatory took over 2 decades to plan and build. It carries an 8.4-meter mirror, and behind that mirror sits the largest digital camera ever constructed, a 3.2 gigapixel eye capable of capturing detail no ground-based telescope has managed before. For most of its life, this machine has been getting ready. Test images, calibrations, engineers checking, double-checking, making sure that when it finally opened its eye for real, nothing would go wrong. That moment came at the end of June this year. The observatory officially began what's called the Legacy Survey of Space and Time, a single, uninterrupted mission to photograph the entire visible southern sky, over and over, every few nights, for 10 straight years. Here's what makes that different from anything before it. Most telescopes point at one thing, a galaxy, a star, a single patch of sky studied for hours, sometimes days. Rubin doesn't do that. Rubin watches everything, everywhere it can see, on a loop that never ends. Astronomers aren't calling it a photograph anymore. They're calling it a movie, the greatest cosmic movie ever made, because for the first time, we're not just looking at the universe. We're recording it, changing, in real time, night after night, for a decade. And that's where this starts to feel different. Because a telescope that looks once can be wrong, or miss something, or catch a moment that never repeats. A telescope that never stops looking doesn't get that luxury of missing things. It sees everything, eventually. So the question isn't really what Vera Rubin is. The question is what it's already found. In just the first few weeks, before the real mission had even begun. Before the 10-year survey officially started, the observatory ran a set of early test observations, essentially a warm-up, just to make sure the system worked. In that warm-up alone, scientists confirmed more than 11,000 new asteroids, not 11,000 possible detections. 11,000 confirmed, catalogued, verified by the International Astronomical Union. That's the largest single batch of asteroid discoveries submitted in over a year. And the telescope hadn't even started its actual job yet. Most of them are ordinary. Rocks drifting through the asteroid belt, unremarkable, harmless, simply unrecorded until now. But 33 of them weren't ordinary. 33 were near-Earth objects, asteroids whose orbits bring them close enough to us that they matter. Close enough that, if the numbers had been different, they'd matter a great deal. None of the 33 pose a threat. That's the official word, and there's no reason to doubt it. But sit with that for a second. 33 objects, capable of crossing paths with Earth's orbit, existed the entire time. And we didn't know. Not because they were hiding, because nobody had ever looked closely enough, long enough, in the right place, at the right time. Rubin looked, and it found them in weeks. That's the uncomfortable math underneath all of this. Space isn't getting more crowded. We're just, for the first time, building something capable of seeing how crowded it already was. The observatory also picked up nearly 400 trans-Neptunian objects, icy bodies drifting in the frozen dark far beyond Neptune, some of them 1,000 times farther from the Sun than Earth is. Worlds of a kind that have been orbiting out there since before recorded history, utterly invisible to us until a machine on a mountaintop in Chile happened to catch the right pixel of light at the right moment. And this was the easy part. This was the observatory barely trying. The real mission, the one built to run for 10 uninterrupted years, is about to scale this up by a factor most people can't really picture. On February 24th of this year, the observatory sent out its first real-time alerts, messages fired automatically to astronomers around the world the moment something in the sky changed. In one night, it sent 800,000 of them. Here's how it works. Every 40 seconds, the telescope captures a new region of sky. That image gets beamed from Chile to a data facility in California, where a system compares it almost instantly to everything captured in that same patch before. If something's different, a new point of light, a star that's dimmed, an object that's moved, the system flags it. And within about 2 minutes of the photo being taken, an alert goes out. 2 minutes. From the moment of the event to a notification landing on a scientist's desk on the other side of the planet. Once the observatory is running at full capacity, it's expected to generate up to 7 million of these alerts every single night. Supernovae, vanishing stars, objects moving where nothing was moving before. Sudden flares from the centers of distant galaxies, where supermassive black holes occasionally wake up and feed. 7 million changes in the sky every night for 10 years straight. Try to hold that number for a second, because it doesn't behave the way numbers usually do. It's not a countdown. It's not a total that fills up and stops. It's a rate, a permanent, ongoing rate of things happening above us that we are now, for the first time in human history, capable of catching almost as they happen. Before this telescope, most of what exploded, flared, or vanished in the night sky simply went unrecorded. It happened and it was gone. And unless a human being happened to be looking at exactly the right patch of sky at exactly the right moment, nobody ever knew. That era just ended. Somewhere above us, tonight, something is going to explode, or flicker, or move. And for the first time, there's a machine on a mountain whose entire purpose is to make sure it doesn't get away unnoticed. The asteroids were the warm-up. The alerts are the system working exactly as designed. But the deepest part of this story isn't about what's nearby. It's about what this telescope was actually built to find in the dark between the galaxies. The observatory carries the name of a woman most people have never heard of, even though she quietly rewrote our understanding of the universe. Vera Rubin was an American astronomer who, decades ago, noticed something wrong with the way galaxies spin. Stars on the outer edges of galaxies were moving far too fast, fast enough that, by the laws of physics as we understood them, they should have been flung off into space entirely. They weren't being flung off, which meant something invisible had to be holding them in place. Something with mass, with gravity, that we couldn't see, couldn't detect, couldn't photograph. We call it dark matter now. Vera Rubin didn't discover it outright, but her work gave us some of the clearest evidence that it was really there. And that the vast majority of the universe's mass might be made of something we still, to this day, cannot directly observe. That's who this telescope is named after. And that's fitting, because the deepest purpose of this 10-year survey isn't asteroids, and it isn't alerts. It's mapping the invisible. Over the course of the survey, Rubin is expected to catalog millions of supernovae, the violent deaths of stars scattered across billions of years of cosmic history. Each one acts like a cosmic measuring stick, letting scientists calculate how fast the universe is expanding and whether that expansion is speeding up in ways that still don't fully make sense. It's also watching for active galactic nuclei, the glowing cores of galaxies where supermassive black holes are actively pulling in matter, flaring with more energy than entire galaxies of ordinary stars. And by tracking how galaxies bend and distort the light passing near them, scientists hope to build the most detailed map ever made of dark matter itself, the invisible scaffolding that appears to hold the entire structure of the universe together. So this machine on a mountaintop isn't just counting rocks and flagging explosions. It's trying to answer a question that's haunted astronomers since Vera Rubin's own data first raised it. What exactly is most of the universe actually made of? We still don't know, but for the next 10 years, every single night, this telescope is going to keep looking, patiently, relentlessly, without pause, for the answer. And somewhere in those 7 million nightly alerts, in that endless stream of flickers and flares and moving points of light, there's a real chance it finds something we're not prepared for at all. 10 years is a long time. Long enough for a machine that never stops watching to eventually catch almost everything worth catching. The asteroids we've already found were just the opening minutes. The real survey, the one that runs for a decade without a single night off, has only just begun. Somewhere above us tonight, the sky is already changing. And for the first time, something is finally watching closely enough to notice. If this kept you thinking, subscribe. We're covering what Rubin finds as it happens.